Good morning to one and all. My name is Sai Baba. Today's my demonstration chapter name is chemical bonding and molecular structure. From that, subtopic is hybridization. First of all, what is meant by hybridization? I am going to discuss. Right. Definition of the hybrid orbital is the process of intermixing of the degenerate orbitals or the orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals. Of equivalent energies and shape. This phenomenon is known as hybridization. So, what is the overall meaning of this hybridization is? That is degenerate orbitals, intermixing of degenerate orbitals. So, and otherwise slightly different energy orbitals are intermixing and redistributing the energy, resulting in the formation of new set of orbitals of equivalent energies and shape. This phenomenon is mentioning as hybridization. That means, what is the degenerate orbitals? Degenerate orbitals are nothing but a same energy orbitals. Suppose I am taking a p orbital. P orbital, it has a 3 number, that is a px, py, pz. And this is one thing. And next one, same energy, how we are mentioning the orbitals of same shell. Suppose I am taking the 2p. 2 is a orbital, otherwise a shell it is indicating. So from that p orbitals energies, that is a px, py, pz, I am taking, and slightly variation means suppose I am taking 2s, 2p orbitals, I am taking 2s, 2p orbitals, right? Otherwise 4s, 3d orbitals if I take, so they have the slight variation in their energies. So those can intermix and form the new set of orbitals with same energies. Those are called hybrid orbitals. Okay. So like that we are discussing the hybridization. Right. So we have some conditions to discuss the hybridization. What is the conditions? Means, right. So first one, right. Only the orbitals present in the valency shell orbitals only participate. So this is the first condition. Second one, small difference in their energies. Same energies, otherwise small difference energies only, energy orbitals only participating, or same energy orbitals, small difference or same energy orbitals can participate in the hybridization. Right. So, but the orbitals which are large difference in energy, they cannot participate. Orbitals cannot participate. Okay. And it is not essential that only half filled orbitals participate in hybridization. In certain cases, what happening? In certain cases, even filled orbitals also filled orbitals of valence shell participate in the hybridization. So, what I am mentioning, first thing, valence shell orbitals only participating in the hybridization. Second thing, the orbitals which are same energy or small difference energy orbitals only can participate in the hybridization. So the orbitals which are having the large difference in the energy, they cannot participate in the hybridization. And always not only the half filled orbitals can participate in the hybridization, sometimes full filled orbitals can also participate in the hybridization. Next one, characteristics of hybridization. So in that first point is, the number of hybrid orbitals are formed is equal to the number of orbitals that get hybridized. That is how many orbitals are forming, that is orbitals how many participating in the hybridization. So that is the number of hybridized orbitals formed is equal to the number of the orbitals that get hybridized. Second point, right, the hybridized orbitals are always same energy, that is equivalent energies we will mention. So right, then second point is, the hybridized orbitals are always equivalent in energy and shape. Right. Third one is, right, the hybrid orbitals are more effective in forming stable bonds than the pure orbitals. So compare with the pure orbitals, so these are having the stable effective, right? And so the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. Right. So next one, hybrid orbitals are directed in space. Right. So on in a specific direction, they are orientation the molecules. So that is, the hybrid orbitals are directed in space in some preferred directions to have stable arrangement. stable arrangement. Therefore, the type of hybridization indicates geometry. Type of hybridization indicates the geometry of the molecule. Geometry of the formula for knowing the hybridization varieties. So what is the formula? V plus M plus A minus C by 2. What is meant by V? V is nothing but a valency of electron in central atom. Electrons in central atom. Valency of central atom. There is a valence electrons present in the central atom. Right. Next one, M. M is nothing but a monovalent atom. Monovalent atoms are examples of what? Hydrogen, fluorine, chlorine, bromine, iodine. These all are nothing but a monovalent atoms. Right. How many in number that we have to write? Then A. A is a charge on anion. Charge on anion. And C. C is a charge on cation. Charge on cation. So, whenever we are substituting the values in this formula, suppose if we are getting value is a 2, then hybridization is sp. If you are getting value is a 3, then hybridization is a sp2. If you are getting value is a 4, then hybridization getting what? sp3. So if you are getting value is a 5, then hybridization is a sp3d. If value is a 6, then sp3d2. If value is a 7, then sp3d3. sp3d3. Right? Now, how to use the formula? Now I am going to discuss. Right? By taking the examples, how to use the formula I am going to discuss. But before that, we have to know what is the valence of the electrons. So simply, if you know the group number is equals to valence of electron. Always remember, group number is equals to valence of an element. Valence of an element. Right. So how to use? Just I will simply discuss. First example I am taking. Suppose I am taking the BeCl2. We have to know what is the central atom. So that central atom is group number is what? Right. Here a central atom is a beryllium. Right. Maximum places what we are considering means the element which are in less in number in given formula, that is considering as a maximum place is central atom. Right. Here central atom is a finally beryllium we have decided. But what is the group number of the beryllium? That we should know compulsory. So here a beryllium group number is 2. Then its valency is a 2 So I am substituting in the formula, that is a 2 plus monovalent atom. Monovalent chlorine is a monovalent atom only, no? How many in number? 2 in number. So then it is a 2 plus. Is there any anion? No. Then 0. So is there any cation? There is a 0. So by 2. Then it is equals to 4 by 2 4 by 2 is equals to how much? 2. Then its hybridization is whenever 2 is coming, that time hybridization is what? 2 is coming means that time hybridization is a sp. Right. So it is like that. So similar way, I am going to do another example simply. CH4. So carbon, central atom is a carbon. So its group number is a 4 then its valence is a 4. Right. Monovalent atom is a what? Hydrogen monovalent. How many in number? 4 in number. Is there any anion cations? No. Then 0 by 2. Then 8 by 2 8 8 by 2 is nothing but a 4. That is a, then whenever the 4 is coming, that hybridization is what? sp3. Then it is a sp3 hybridization. So okay. So these are the neutral molecules. These are the neutral molecules. Suppose if charge is coming on the molecule, means suppose I am taking my third example, that is a NO2 plus. So there is a charge. Which charge? Positive charge. Positive charge means that is a cation. So cation. Then how to use? Means, so first is the central atom is a N number. Central atom is, what is the group number of the nitrogen? That is a fifth group. So then 5 plus. Is there any monovalent atom? Oxygen is a divalent atom. That we should know compulsory. So oxygen divalent atom, there is absence of monovalent. Then 0. So is there any anion? So no anions. Then 0. Is there cation? Cation is there. How much? 1 positive charge by 2. Then 5 minus 1, that is 4 by 2. Then hybridization value is 2. Hybridization is what? 2 sp. So 2 is coming. Then it is a what? Sp. Right. Then so cation coming. Then we are calculating hybridization of the molecules like this. If anion present on the molecule, suppose I am taking NO3 minus, then same here, nitrogen having the valence is a 5, so oxygen is a divalent atom, then it is a 0. So anion means then what? Plus A means plus 1. So cations are 0, then by 2, then 6 by 2 means value is a 3. Then hybridization is what? Hybridization is what? sp2. Then next one is, so if molecule having both monovalent and divalent, then how to do? So example is xenon oxytetrafluoride. So xenon group number is what? 8. Group number is 8. So plus. So in formula we have mentioned valency plus monovalent only, but not divalent. Here oxygen is a divalent. Then so I am not considering the divalent atom. So simply I am taking monovalent. Monovalent are how many? Fluorine is a monovalent atom. Just check it, whatever I have given previous, just go back and check it. Then there is a monovalence are 4. So is there any cation anion? There is no cation, there is no anion. Then by 2. Then 12 by 2. So 12 by 2 is nothing but a 6. So then hybridization is what? sp3d2. sp3d2. So this is the hybridization. Suppose another one example finally I will discuss. That is a SO4 minus 2. Here central atom is a sulfur. Sulfur group number is what? 6. So group number we should compulsorily learn. Right. So sulfur group number is a 6. There is an absence of monovalent atom, but anion is there. How much? That is a 2. Cations are 0. Then by 2. Then 8 by 2. That is a what? 4. Then hybridization is a what? sp3. Right. Not only the formula, by using the another one method also we can find out the hybridization of the molecule. That means based on number of bond pairs and number of lone pairs also we will find out the hybridization. But in previous year questions they have asked given the molecule and how many lone pairs and how many bond pairs they are asked. So by using that lone pairs and bond pairs also how to find out the hybridization I will give. Right. Before that we have to know something. That is what is the valence, what is the valency. So valence and valency. So simply valence is nothing but a electrons present in outermost shell. Present in outermost shell is a what? Outermost shell. That is a valence. Right. Valence is a number of combining capacity. Number of electrons combining capacity with hydrogen. Number of electrons combining capacity with hydrogen atom. Okay, that is the valency. How many unpaired electrons are there? how many unpaired electrons are there, that only participate considering as a valency, and those only participating in the formation of the bond. So based on that, here we have given group number valency. For first A group, that has its valency is a 1, second A group valency is a 2, third A group valency is 3, fourth A group valency is a 4. But again from fifth A is a valency is a 3, sixth A is a valency 2, so seventh A valency 1, eighth A is a 0. Right? By using this, I am going to discuss how to find out the number of lone pairs, number of bond pairs. From that, how to find out hybridization. First example, I am taking ClF3. He is asking number of lone pairs in ClF3. Number of lone pairs in ClF3. Then, so how to calculate? So first of all, ClF3 I am taking. ClF3. Right? So chlorine. So in this chlorine, so 7 electrons are there. 3, 4, 5, 6, 7. So monovalent atom is a fluorine. So fluorine is a 3 fluorine atoms, like this I am writing. Right. So remaining 2 lone pairs. But we know we can consider bond pairs and lone pairs in the hybridization, but not pi bonds. That we have to remember. Right. So then totally 3 bond pairs are there, 2 lone pairs are there. 3 bond pairs, 2 lone pairs. Totally is a 5. So total is a 5 means what is that? sp3d is the hybridization. sp3d is, these are the previous year questions. What they have asked, so that I have written and I am explaining. Then next, in NEET 2013 they have asked, what is that? 3 bond pairs, 1 lone pair example is what? That is not this is PCl3 only I am taking example. 3 bond pairs and 1 lone pair consisting molecule is a which one? Right. Here I am taking the directly PCl3 molecule. Right, PCl3 molecule. So in that PCl3, what I am considering? Phosphorus is a what am a fifth group. 1, 2, 3, 4, 5. 3 chlorine atoms. 3 bond pairs. 1 lone pair. This is it. Then so 3 bond pairs are there. Right, 1 lone pair is there. Lone pair. Totally 4. So totally 4. Then hybridization is what am I? sp3 is the hybridization. sp3 is the hybridization. So like this we can find out different molecular hybridization. And in following below question what he is asking, maximum number of lone pairs in xenon. Maximum number of lone pairs in xenon. So xenon components 4. 1, 2, 3, 4. These 4 molecules we are taking. So which has the maximum number of lone pairs we are going to discuss now. Right? So from that, first one I am calculating. Which one? Xenon difluoride. So xenon is a 8th group no 3rd, 4th, 5th, 6th, 7th, 8th. 2 fluorine atoms. 2 fluorine atoms, how many? Totally 3 lone pairs. That means here how many totally? 2 bond pairs are there and 3 lone pairs are there. So totally is how much? 5. Hybridization is what? sp3d. Then xenon tetrafluoride. In xenon tetrafluoride 1, 2, 3, 4, 5, 6, 7, 8. Then 1, 2, 3, 4, 5, 6. Sorry. 4 no? Only 4 only. Right. Then this one and this one. So bond pair this one. This is a bond pair. 1 bond pair only. This is a 1 bond pair. So totally how much? 4 fluorine atoms are there. 2 lone pairs. That means 4 bond pairs are there and 2 lone pairs are there. Totally is a 6. Then it is a sp3d2. Xenon hexafluoride. In xenon hexafluoride again 1, 2, 3, 4, 5, 6, 7, 8. So 6 fluorine atoms. And 1 lone pair. So totally 6 bond pairs are there. 1 lone pair is there. Total is a 7. Then hybridization is what? sp3d3. Then finally xenon trioxide. 1 2 3 4 5 6 7 8, right? So oxygen is a divalent atom, right? 3 bonds, right? 1 lone pair. So totally here one is a sigma bond, another is a pi bond, amma. That's what I am considering, only sigma bond. 2 bonds including one like this I am giving, no. One is forming the sigma bond, another is a pi bond. But pi bond is not participating in the hybridization, only sigma bond only participating. Right? Then totally is a 4 bond pairs only. 4 bond pairs. So then its hybridization is sp3 I am considering. Right? So from this, which has a more number of what he is asking, lone pairs, amma. Lone pairs. So xenon difluoride having 3 lone pairs, right? Xenon tetrafluoride having 2 lone pairs. Xenon hexafluoride having the 1 lone pair. So here also 1 lone pair. Maximum is xenon difluoride having the more number of lone pair of electrons. Right? That means from this, by using the bond pair, lone pair also we are find out in the hybridization. This is the another one way, namma. Right? Here clearly we will get how many bond pairs, how many lone pairs. By using the Vesper theorem, we will give the structure to the molecule also. Right? Right. Yes. Now, how BF2 molecule will form and how sp hybridized orbitals will form, how the fluorine orbitals can overlap with the sp orbitals. So overlapping of the orbitals we are going to discuss. So first example is I am taking, that is BeF2.